Welcome back to day 28 of System Design. Yesterday, we built chat applications by passing lightweight text messages back and forth. Today, we face a massive engineering hurdle, moving a 5 GB video file to millions of users simultaneously. The naive approach is what we call the MP4 problem. If you treat a 2-hour movie like a standard server download, you're trying to shove a massive, inflexible block of data through an unpredictable network. The fatal flaw here is fragility. With a standard single file download, if a user's mobile connection drops for a single microsecond, the connection breaks. That multi-gigabyte transfer fails entirely and forces the user to start all over from zero. Mobile networks are inherently unstable. A static file download cannot survive this reality. We need an entirely different, distributed architecture to handle the load. Back on day 9, we explored content delivery networks. To eliminate baseline latency, we first have to physically cache these massive files on servers located geographically close to the user. This diagram outlines that structure, showing how video streams directly from a local edge server, the CDN, straight to the client's laptop, phone, or television. But physical proximity alone doesn't solve the download interruption issue. The continuous file structure itself has to be destroyed and rebuilt. Our first system hack is video chunking. Before the video ever reaches the CDN, the backend server chops the continuous movie file into a series of independent 2-second segments. If the network drops while streaming a chunked file, the client only loses the current 2-second segment. The previous chunks are already safe on the device, and the player can simply request the missing piece again. By isolating network failures, chunking replaces a single massive point of failure with thousands of recoverable microtransactions. We still have a bottleneck. A 2-second chunk of raw 4K video requires significant bandwidth, making it far too heavy for a weak mobile connection to process in real time. To fix this, we apply a multi-resolution hack. The back-end transcoder generates multiple versions of every chunk, creating a matrix of storage options for different hardware constraints. Large streaming platforms use a directed acyclic graph, or DAG, to manage this. The DAG creates parallel processing pipelines, simultaneously encoding the original video into 4K, 1080p, and 480p formats. The output of this transcoding workflow means every single 2-second interval of the movie now exists in multiple distinct sizes and quality levels. This heavy back-end preparation guarantees that there is an optimal, perfectly sized file ready for any real-world network condition a user might encounter. At this stage, we have to flip our understanding of the system. The server doesn't actively push this video to the user. Instead, the video player on the client's device is an active, intelligent agent constantly pulling data. The player uses adaptive bitrate streaming, or ABR, to continuously measure the user's exact download speed in real time. Imagine a user watching a movie on a train, suddenly dropping into a cellular dead zone as they pass through a tunnel. The ABR logic detects the drop in bandwidth before the video can buffer. It instantly stops requesting the heavy 4K chunks and starts pulling the tiny 480p alternatives instead. To find these alternatives, the player relies on the HLS protocol. The server provides an M3U8 playlist file, a dynamic menu that points the player to the exact URLs of all the different chunk resolutions available. Adaptive bitrate and HLS create a highly responsive, pull-based architecture. The client actively dictates exactly what it needs, chunk by chunk, to survive constant network fluctuations. When you combine edge CDN caching, chunking, parallel DAG transcoding, and HLS, you turn a rigid, fragile media file into an agile, adaptable stream. Instead of wedging a massive boulder through a pipe, the system breaks the data down into a fluid stream, flowing seamlessly around network bottlenecks. Now we can stream pre-recorded 4K movies anywhere. But what if the video isn't pre-recorded? What if we are building Zoom and latency must be 0? Tomorrow, day 29, we dive into WebRTC and peer-to-peer streaming. Hit subscribe.